Hello again. This video is on finding the area of objects using linear transformation and determinants. This is the last video on the section on determinants. Yes, I know. I said the last video was the last video, but this is really the last video on determinants. So let's go ahead and read this first paragraph that's in the book to get started as a motivation. It says, determinants can be used to describe an important geometric property of linear transformations in the plane and in R3. If T is a linear transformation and S is a set in the domain of T, then T of S is the image of all the points in S. We are interested in how the area or volume of T of S compares to the area or volume of the original set. And then they say here, for convenience, when S is a region bounded by a parallelogram, they'll just call it S to refer to the parallelogram. So here's the theorem. It says, again, T goes from R2 to R2, be a linear transformation defined by a 2x2 matrix A. If S is a parallelogram in R2, then the area of the new object, how it is going to be related, is the area of the original object times the determinant of A, that matrix. You can also do this with volume as well. Okay. If you're interested in the proof, they have it here in the book. We'll just slightly go through it. So it says, consider the 2x2 case. That's this one, with A being A1, A2 vectors. So that's the matrix. A parallelogram at the origin of R2, determined by vectors B1, B2, has this form. S is equal to some S1, B1 plus S2, B2, where S is between 0, 1, S1, and S2. This makes sense because here's B1 and B2, and here's the parallelogram that forms those two. And any point inside here is going to be, well, this point right here is the endpoint, that's B1 B plus B2, and all these points are fractions of that, aren't they? So for instance, this one would be B1 plus half of B2, or this one right here would be half of B1 plus half of B2. So that's where they got that. So the image of S under T consists of the points in this form. So let's just find T of a point in here. And because it's linear, we can write it this way. And this is the definition because we know that T of X is going to be AX. So we get this. And that, by the way, is T of S. So we could have wrote this in set notation too. So this is T of S, for instance, is all these points where you have that. So because of that, it follows that T of S is the parallelogram, is also a parallelogram because it looks just like this form, determined by the columns AB1 and AB2, which by the way is just AB. So the area of this T of S we know is just the determinant. So we can say this is the determinant of A times the determinant of B, our last section. And we know the determinant of B is a parallelogram, right? So it's determinant of A times the area of S. This theorem that we have up here actually holds, let's make this smaller so we can see the whole thing, actually holds whenever S is in a region in R2 with finite area, or a region in R3 with finite volume. So we're going to just do the area example. It doesn't have to be a parallelogram. If you are interested in why, there's a whole explanation on page 185 in our textbook. To see an example of this, let's look at example 5. Example 5 says, let A and B be positive numbers and find the area of region E. So region E here is bounded by the ellipse with the equation x1 squared over a squared plus x2 squared over b squared equals 1. And since we know the area of a circle, or what they call this disk here, we can use that transformation to find the area of the ellipse. So what I'm going to do is I'm going to let E be this region. So what is it? And D be this region. So E is, let's call it x1, x2, where it's going to be less than or equal to 1, right? Because when it's equal to 1, it's the actual ellipse. So we want the whole area. And then let D be our circle. u1 squared plus u2 squared is less than or equal to 1. I'm going to call it u1 and u2 because I want to relate the two. So how I'm going to relate the two is I'm going to say let's let u1 be x1 over a and u2 be x2 over b. So therefore, if you pick an arbitrary x, x1, x2, if you solve for x1 here, you get u1a, and the same thing here, u2b, which, by the way, can be written as this matrix times u. Because if you look at this, this is just a1u plus 0, and this is just 0 plus bu2. I said a1, but au1, and then bu2. So that's my transformation. So what I'm going to do is I'm going to let A be this matrix and T be my transformation from R2 to R2, because this is an R2 and that's R2. And it's going to be defined by T of U, because that's a U, is equal to AU. And by the way, X we know is A times U, and over here AU we know is T of U. So that tells us that E, which is, let's make this smaller so we can see that, E is the image of this unit circle. So right here's the unit circle, and the X is the image, the E is the image of that unit circle, where A is this matrix. So it says it holds whenever S is in the region with R2. And what does this region say? It says if T is a linear transformation determined by a 2 by 2 matrix, and S is any region now in R2, this will still hold. So let's write that. The area of T of S. So in our case, what do we want? We know that we want that the area of T of D is equal to the determinant of A times the area of D. So that's exactly what that said. In case instead of a S, it's a D. Okay, and this we know, the area of T of D is the ellipse. So this is the area of the ellipse. And then the determinant of A, so here's A right here, that is just AB. And the area of the disk, well, the area of the disk is pi r squared, and r is 1. So there it is. We just found the area of the ellipse. Lastly, let's look at this practice problem. In this case, we're now going to let S be a parallelogram defined by these two vectors, and A be this matrix. So we're going to compute the area of the image of S under the mapping T of X equals AX. So you can pause it, try it, see if you can do it, and then come back when you're ready to see the solution. So here's the solution. So first they took the determinant of 1351, it's the book solution, and then they found the determinant of A, which was 2, and the theorem says that the area of the image of S. So this is equal the area of T of S, we know, is the determinant of A, since T of X equals AX, times the area of the S. And we know the determinant of A is 2. We know that the area of S, it's a parallelogram, so the determinant is, that's just going to be the determinant of the 1, 5, 3, 1. So you have it. And that concludes this video and this section.